Thank you for the introduction. I'm from the Stony Brook University. Actually, my group has been using the NIST since 2000. So we started from the neutron reflectivity, SUNS, and now we're using the neutron spin echo and the neutron backscattering. So I really appreciate the guidance from Michi at the NIST and the guidance from the Beta at the GNOV. And the last 2 months ago, we had the opportunity to work with Laura at the Oakley. So we stayed there 15 days at the Tennessee. So it was a really exciting opportunity for us. And so today, yes, I want to talk about our ongoing research, especially we're using the neutron scattering, neutron spin spectroscopy. And our target is the automobile tire. And our focus is here. This is the polymer chain at the filler surface. We want to see what's going on this interface, polymer and the filler interface. And our target, especially this one, it's called the bound polymer. So some polymer actually physics-solve onto the filler surface. And this plays a crucial role in the mechanical property. Even the thickness is only a few nanometers, but this is the key for the automobile tire, especially mechanical properties. So I want to show you how we design the system, right? How we did the experiment, and then how we did the data analysis, and then how we get the data published. So let me show you. Okay, so as you know, the automobile tire, right, automobile car is the integral part of our society, right? Even you have a Tesla, but if you don't have a tire, it's useless, right? And then only the tire is the tire is the only component to attach to the road, right? So the tire is really important for the safety is issue, like economy, right? And the grid condition. So we have to do something with the automobile tire. And it's a more important thing is now sustainability, right? So we have to make new automobile tire, especially synthetic rubber, with balance and then performance, right? So then this is the automobile tire. So if you look at the microscopic scale, tire is kind of complicated because the reason for that one is, this is a polymer structure. The polymer has a structure from, let's say, 1 nanometer to micron scale. And the different structure has a different dynamics, okay? And then there is the filler. So filler, most likely, this is a carbon black system, carbon black or silicon nanoparticle. They also have a hierarchical structure, something like this. So the different structure has a different dynamics. So now the question here is, which part of the structure are the key to control the property? For example, here, right? If we want to control the field efficiency, what the company does is most likely they want to control the structure like micron scale. Or if you want to change the grip, something like this, or impact fracture structure, like an nanometer scale. But at this moment, there's not exact relationship right, between the structure and the dynamics and the functionality. Because again, we cannot see this structure, right? So we need a tool. That's why we are using neutron scattering experiment, okay? So I want to show you the challenge from the polymer point of view. So as I said here, this is the carbon black here. The size is about 100 nanometer. I'm not sure whether you can see or not, but here, outside of the polymer, the surface, that's what we call the bound rubber, this bound rubber. So the thickness is a couple nanometer. We cannot dissolve this polymer. It's strongly attached to the filler surface. And then believe it or not here, this bound rubber plays a crucial role in the reinforcement property of the polymer. So I want to show you the data here. See, this is the typical rubber sample, I mean the automobile car sample. So this one is, we measure the mechanical property of the tire, which is composed of this one is a polybutadiene. The molecular is 500K. And then we use the carbon black system. And then this red curve corresponds to this one is a stress strain curve. So we stretch the polymer and then we measure the mechanical property. That's the stress, right? So this is a typical behavior of the automobile tire, but I just want to tell you, This one, typical automobile tires, they are cross-linked, the polymer itself. This one we did for the simplicity, right? And then here, this blue curve corresponds to the same component. It's the same molecular weight of the polymer, same carbon black system. But the only difference is this carbon black, we heat it before we mix with the polymer at the high temperature. So what's happening here is this carbon black, right? At the surface, there is a surface functionality, including the carboxyl group or something. So that group is gone at the high temperature. So what we found is actually, after the process, there is no bound polymer. So if we use the carbon black, we call it graphite carbon black system, mixed with the polymer. So here's a mechanical property. As you see here, it's much, much weaker compared to the regular carbon black system. So this is the effect of the bound rubber. See, as I said, bound rubber is only a 2 nanometer, but they can control mechanical properties. So this is our motivation, for the research. So the question is, what's the role of the bound rubber system? So as I said here, basically, the bound polymer and the polymer matrix, the same component, right? Only difference is the bound polymer is strongly absorbed onto the filler surface, right? So that means it's basically same polymer, unless we label something like this one. Here I show the bound rubber in the left for our eyes. Unless we do something like this one, we cannot characterize the bound polymer system. Here we use, again, neutron scattering, especially we use the deuterated polymer for this one. I want to show you how we prepare the sample. But at the same time, this bound rubber is composed of the 3 components. If you look at much smaller length scale here, this is the bound polymer. So we call this is a train, this is an attached component. And they also compose a loop, and they have a tail. So it's more heterogeneity at the microscopic scale. So we see more dynamics, and then structure become more complicated. Okay, so today I want to show you how we use the neutron scattering, especially neutron spin echo, neutron back scattering, to see or to highlight the structure of the bound rubber here. This is a neutron beam, and then from there we can get the structure and the dynamics information. And then at the same time, I'm not sure whether I have time, but if I have time, I can also talk about this one is a different polymer system. This one is the system is the carbon fiber. Carbon fiber filled with the plastic. The plastic is isotactic polypropylene, which has been used for the many applications. So this one, again, we also using the neutron backscattering, and we also combine with the molecular dynamics simulation. Okay, so I'm going to show you what we get. So most likely this part is that I want to show you how this bound polymer is formed on the filler surface. This one is more like the structure and the dynamics, and then how they are related to the mechanical property. Okay, so the polymer group, we did this one, remember? So first we have to make sure we have a contrast. So then in this case, right, so here, this is a carbon black system. Again, as I said, the outside is the bound polymer, right? So we want to make a contrast by using depolymer. That's what we call isotope labeling. So here I use, right, by using the NIST website, I calculate the SLD exactly like what you did, right? So here we use, for example, hydrogen HPV, that's the left. And according to the website, yes, this is SLD, 10 to the minus 7, right? If we use a depolymer as a matrix, SLD is a 5.7. And the good thing for here is that if you use a carbon block system, carbon block system, SLD is pretty much same as depolymer system. So what we can do is here, we can say this one is a contrast match experiment. So neutron only see bound polymer. Okay. So then here's more system. We use the carbon black system. The size is about 100 nanometer. And then again, this one is we don't use the cross-linking process yet. We will do it later. And the filler loading is at the 20%, which is below the population threshold. The reason for that one is we want to see individual van der Waals structure and van der Waals dynamics. That's why we use this one, 20%. And again, the HDPB. And then again, as Liz said, we have to characterize the structure before spin echo experiment or before the SANS experiment. So we use this one, and then we characterize the thickness. It's about 5 nanometer. Okay, so this is how we prepare the sample. So we start with the HPB and then PB. We mix together. So, right? So this is the polymer. This is the typical automobile type, for example, right? After this one, as I said, this bond polymer, it doesn't dissolve. Even we use for example, this one is a tolerant. Tolerant is a good solvent. So we thought that we can remove everything, but not the bond polymer. So by doing this one repeatedly, so we can make bond rubber layer coated carbon black sample. After this one, yes, we mix with the DPB, that's here. So now this is a sample for the Newton experiment. So as you see, we have so many D polymer, and as we discussed, right, expensive. It's just kind of crazy experiment unless we have money. I don't have money, but the good thing was this is a collaboration with the industry, right? So if you have an idea, if you have money, you have to convince the industry. This is one way, or you have to get the funding from the NSF, but the NSF money doesn't allow too much for the sample, right? So you have to find sponsor. That's also another thing as a PI. Okay. So this is the sample. Okay, next. Okay, this one, I'm not sure how much I have time, but again.
You have time.
Are you sure?
Yeah, I am sure.
10:06.
I'll let you know, like.
Right. But they need the time, though. They need the time for the preparation.
Yeah, going like,
It's
okay.
So I kind of skip it. So this one is again, before we do the real experiment, I want to characterize the structure and the bound rubber structure. So that the way what we did is we use this is a carbon block system with the bound rubber. Instead of doing the D polymer, we use the D tolerant. And we want to see how the polymer chain swell. That's here. And at the same time, of course, we want to see the dynamics of the polymer chain here. So this is the SANS experiment. And then at the same time, we did this one is the spin echo experiment. And then in the polymer group, right, we did using, remember, segmental dynamics. We used the large fit with the Antonia. And in this case, but we realized, segmental dynamics is not the case. And then again, I did the search of the paper, and then our legend. He published a paper in the Physical Review Letter in the 1993. And this is it's not the segmental motion, it's more like a corrective motion. It's like a jellyfish. The chain stretch, right? And then after the chain squeeze back, stretch, squeeze back. That's what we call freezing mode. Okay, so this is the dynamics in the solvent, the bound polymer system, right? So now the question is, how about the real system? But again, I learned from the Liz, and then she was saying, yes, we have to do lots of experiments before the spin echo or SANS experiment. So this is what we did. And this one is, for example, carbon block structure itself. So the carbon block itself is, again, this is the carbon block primary particle, right? This is the size. And at the surface, they have we call it surface fractal structure. It's not the smooth, it's a bumpy, something like this one. And of course, they have an aggregate structure. We characterize this one beforehand. And then this one is the actual sample. So this one is again here, right? Our system is a carbon block. Outside is the H polymer. And this one is in the DPB polymer. So this is a SANS data. So then I don't go into detail here, but we have to characterize the structure first, right? At this moment, because of if the carbon block itself is monodisperse, we can use, remember, quotient model to fit the data. But unfortunately, this one, the carbon block itself has a polydispersity. So we couldn't use that one. So instead, there is the equation which we use. This one we use the, it's called a unified equation to describe hierarchical structure of the filler. So we can characterize the filler. This is an individual particles. It's called, again, this one it's about the Guinea regime. There's another Guinea regime that comes from the aggregate. So we did that one, right? And then as you see here, this dotted line corresponds to the theory. Theory based upon the size of the primary particle and the aggregate. So now you see the difference. By the way, this one, remember, we have to subtract the background, incoherent. We did it, right? And at the same time, we also subtract the background. Background in this case is the deep carbon block system in the DPB without H point. So we subtract it. But as you see, we still see the excess scattering. Right? So that excess scattering comes from inner heterogeneity. So, right, so this is the bound polymer. So within the bound polymer, there is a heterogeneity, right? That gives rise to the scattering. So we want to characterize this structure. Okay, so this is an excess scattering as a function of the Q, this one. So again, right, the sun's experiment, remember, we need a structure model, right? So the first thing, we did is, yes, first we assume this is the bound polymer chain, this is a carbon block system. We first assume, because again, the size of the carbon block is 100 nanometer compared to the thickness of the bound rubber. This is about 7 nanometer, So that's why we consider this carbon block itself is the planar substrate, number one assumption. And then again, we search the paper. I don't go into the theory behind, but again, based upon the T's, yes, we make the model, we calculate the scattering intensity, and then we fit the data. So this one corresponds to, the black one, dot line corresponds to the calculated scattering profile based upon the density profile, which we assume. So that based upon the data, we found that, looks like a bound layer is a two components. One component there is we call it inner layer. The thickness only like less than 1 nanometer. But as you see, this is volume fraction of the H. See here, as a function of the distance from the carbon block surface, right? Within this regime, the volume fraction of the H polymer is 1, which means there is no penetration of the matrix polymer within this regime. The second is here, this regime, so this is outer regime, right? This outer regime, they miscible somehow with the matrix polymer because of D go into the bound polymer, right? So that's why now you can see the volume fraction of the H become less. So it's like a interpenetrated within this regime. So they form like a broader interface. So now we did this one, right? So now we characterize the structure. So now it's a time for us to do dynamics. And then so in here, right? So we did the segmental motion, right? That's here. And this is the polymer motion because again, this dynamics play a crucial role in the mechanical properties. So we want to see how the segmental dynamics or again, shear diameter, remember, how that control the mechanical property. So again, start with the loss, right? So we did this one, right? So for this one, yes, as Madhu said yesterday, we used again neutron backscattering experiment. The point is, yes, we use exactly the same system, right? But we have H component, hydrogen component. That's why we can see the signal from the H that come from the bound rubber. Right. So see, this is your favorite SQE, dynamic structure factor, at 75 degrees at the given Q value. So we fit the data, right? I don't go into the detail here, but we fit the data. So then it looks like there is a two component, as Madhu explained. So there is one component which is the elastic component, and there is the we call the mobile component, and we use this one again, KWW function, right? So we use the KWW and then get this one is the relaxation time of the segment, and at the same time we're going to get this exponent, right? So we assume this one is the IQT, do the Fourier transform. Right? This is a Fourier transform. So now we can convert into the SQE. That's exactly what we did in the class. All right. So we got this tau and then gamma as a function of the Q, and then see what we can see. Okay. So this one is the characteristic time, right, as a function of actually Q. And it's all right. So again, we keep discussing this one, right? So we have a new polymer system, but we want to know whether or not this behavior is usual or unusual, right? So for this time, we prepared a sample, which is again free polymer system. So I mean, it's a mix, same amount of the H polymer in the system, and again DPB. Right? So the HPB is 3%, 97% is the DPB. It's a polymer blend system, so that we can discuss about how the free polymer chain behave in a polymer matrix. So this is that's the blue correspond to the free polymer chain, red correspond to the bound polymer chain here. So you see, I don't go into the detail here, but again, this power law, characteristic relaxation time, again, this gamma corresponds to the exponent, which we use for the KWW. If you see something like this behavior, this is the indication of the Laus model. So, right, so as you see here, between the bound polymer and the free polymer chain, there's not much difference. This is the data which we got based upon the neutron backscattering data. So again, average segmental motion is the same. So this is the first message from the neutron experiment. Okay, so now we did the backscattering. So we measure the segmental motion. Now let's move to chain motion. This one. So we did this one exactly, right? Remember? So now we want to talk about size of the tube, right? Because that comes from polymer entanglement, right? Because of the entanglement, right? Polymer chain is somehow confined within the tube. So we want to understand, we want to estimate the size of the tube, right, by using the neutron spin echo experiment. So now here, remember, SQT as a function of T. So this time regime corresponds to segmental motion. So we fit the data, with the equation, right? And then something around here, this we call the crossover time. We estimate the time. Right? So we estimate it's about 40 nanoseconds. So again, after the time, that's what we call the local rotation time. Now we start to see the effect of the tube diameter. Right? So I don't go into the detail here, but again, I use exactly the same formula that Antonio provided right here. So the only difference here is because again, we do know that within the bound polymer, there is the immobile component, which means the polymer doesn't move within the time regime of the experiment. So because of that, we also consider diffraction. So that means that even we change the time, actually SQT is kind of constant. That's what we call the immobile component, right? So we found that one based upon the backscattering experiment. So we consider the volume fraction here. So from that fit, basically we can get how much is the actual immobile component within the bound polymer system, number one. Second is this tube diameter. So, okay, so this is the two parameter based upon the fit. So here, this one is the immobile component as a function. This one, we change the time as well. So there is the immobile component within the bound polymer system. For example, almost like 30% of the component is immobile within the time range of the spin echo. So most likely this component the train component, which attached to carbon block system. So this is an immobile component. They cannot move. But outside region, it's more like a loop until they move. And then they behave like free polymer chain. So this is, for example, tube diameter as a function of temperature. So we see a little bit weak temperature dependence, but overall behavior is pretty much same as the bulk, as a free polymer chain. So from this experiment, we can conclude that bound polymer chain, actually they move like free polymer chain. Okay, I have fun. Okay, but this is very important for the automobile tire, for example. So that means this is the bound polymer. There is the free polymer chain, right? So what this neutron spin echo data tell us is they have an interaction. So the bound polymer chain, they interact with the free polymer chain so that the interface between filler and free polymer chain, it doesn't disconnect. They have a really broad interface, which is good. The reason for that one is if we consider the lava, right? So lava itself, the polymer itself is weak, right? So if there is the local stress applied to the lava system, they cannot hold. The polymer itself doesn't hold. So instead, the polymer want to transfer the stress to the film. This is how the reinforcement works. Okay, so that's why I'm saying, if this interface between the filler and the free polymer surface is disconnected, this doesn't happen, right? So energy transfer doesn't happen, but according to, again, Newton data, actually for the lava system, they have a really broad interface so that the energy transfer is possible. So this is a kind of unique capability or unique, I think, the characteristic of the lava system. So since I don't have much time, so unfortunately I have to skip it, but okay, so I just go briefly. This one, this is a similar experiment, but instead of using the Newton spin echo, we use the backscattering. The reason for that one is, again, right, same concept. Instead of using carbon block system, we use this one is the carbon fiber. Carbon fiber. So we will understand the dynamics of the bound isotactic polypropylene on the carbon fiber system, right? But again, this one is a wizard matrix because, again, we need money. I don't have money at the time, so instead, I was using molecular dynamic simulation. The reason for that one is, again, remember, the length scale and the time scale is completely overlapped with the backscattering data. So we can use as a complement, right? So I don't go into here. But, okay, so this is, another reason why we want to use molecular dynamic simulation is because, most of the time, if we show just as Newton data, X-ray data, people say it's boring because just the IQ, SQ omega, right? Uniqueness or MD simulation give us the visual structure, something like this one. So then of course we can characterize the structure this one. Right, so that according to like a quantitative data analysis, we found that this one is the isotactic polypropylene, and this is the carbon fiber, and the white corresponds to the hydrogen, and then green corresponds to the carbon chain. So we can see actually both, right, backbone chain and the side group, they lie flat onto the filler surface, and because, right, if the polymer has that kind of structure, they lose the entropy because that's the confinement. Right, but at the same time, this polymer chain gained the entropic interaction by having the contact with the carbon surface, here, right? So each contact has most likely KBT energy. So if you have more contact, something like this, they gain more interactive interaction. So as a result, entropy contribution is greater than the entropic loss. So that's what we believe. This structure is kind of stable at the filler surface. So the polymer is kind of smart. They understand the situation and they try to accommodate themselves to minimize the free energy. That's this one. Okay, so, okay, this may be the last one. Okay, so this one, right? So I was talking about the bound rubber system here, right? But again, if we increase the filler concentration, what's happening here is, again, the distance between the filler becomes smaller and smaller, right? So this bound polymer, this one, some portion are absorbed onto the neighbor nanoparticles. So what's happening here is that they form, it's called a bridge structure, right? Because of the bridge, now the nanoparticle has a percolation. So then, as you might know, the percolation is the most important contribution to the mechanical property. So we are now using actually X-ray to see the dynamics of the filler, not the polymer, right? So the X-ray is sensitive to the filler, right? So I have to behave because again, this is a neutron, facility, so I don't talk too much about X-ray. But if you are interested in here, please read the paper. So that we will describe how the structure and the dynamics and then property. This is the structure by using the small lung X-ray scattering. This we call the X-ray photon correlation spectroscopy. It's like an IQT, this one, right? But again, this one is a filler dynamics instead of the polymer dynamics. And this is the lava, right? So the time scale of the XPCS is pretty much same as the rheology experiment. So we can correlate macroscopic property and the filler dynamics. And then there is the theory behind. So, okay. So again, I hope I show the data, right? How the neutron experiment is the key to see the structure. But again, as I said, that there is we call it hierarchy structure, right? So if we want to understand again structure, dynamic, and the mechanical property, we have to understand as an entire, as a whole, right? So maybe in neutron experiment, we can probe this structure regime, or maybe the dynamics regime, but we have to integrate different techniques so that we can understand the relationship in more detail. Okay, so I think that's my message. Okay, so this is the collaborator. Again, I appreciate my Stony Brook team, and I also appreciate again the scientists here, and Vera, and of course Laura too, right? And yeah. Okay, so finally I want to close the funding situation. All right, with that I will finish my presentation. Thank you.